Now let's look at a very similar problem, namely number 62. So we need to sketch the graph of the function g of x equals to x plus absolute value of x. We need to find out the values of x where g is differentiable, and we need to find a formula for g prime. Okay, so again, how do we deal with the absolute value functions? Well, we just write it as a piecewise function. So if x is greater or equals to 0, in this case, absolute value of x equals to x. So g of x is going to be equals to x plus x, and the answer will be 2x. All right. On the other hand, if x is strictly negative, so in this case, absolute value of x equals to minus x. So then g of x is going to be equals to x minus x, and the answer will be 0. So therefore, we have got the piecewise function g of x. It takes 2x when x is greater or equals to 0, and it takes 0 when x is strictly less than 0. Okay, so to draw the graph, let's first start with the xy coordinates. So this is my xy coordinate, and g of x equals to 2x. Well, 2x basically looks like this, so it will be a line of slope 2, but because we only need the parts when x is greater or equals to 0, so that we have this part over here. So that will be a line of slope 2. And when x is less than 0, g of x takes 0. Well, 0 is simply this horizontal line, but because we only need the part when x is strictly less than 0. So that's why we only need this part over here. Okay, so this will be the graph for y equals to g of x. All right, so that finished the discussion of part A. Well, for part B, so we will just use the previous principle without justification. So let's directly compute g prime of x. So if x is strictly greater than 0, so in this case, limit of g of x plus h minus g of x divided by h as h approaches 0. So because now x is a generic number, so then I will just use the same formula for g of x plus h and g of x. So g of x equals to 2x. So g of x plus h will be 2 times x plus h. So I will skip the computations, but then at the end of the day, what you get is a constant number 2. So if x is strictly greater than 0, g prime of x equals to 2. So that's what we have obtained here. Similarly, if x is strictly less than 0, because now my x is a generic number, so in this case, both g of x plus h and g of x, well, both these guys are going to be 0. So that will be 0 minus 0 divided by h as h approaches 0. So then, well, the answer for this is going to be 0. So that way we see that if x is strictly negative, g prime of x is constantly 0. Okay, now let's look at what happens if x equals to 0. So because now 0 is a critical number for this piecewise function, so we need to look into the left-hand limit and the right-hand limit. So let's first look at the right-hand limit. So if h is approaching 0 from the right, then my g of 0 plus h minus g of 0 divided by h. Well, in this case, because my h is positive, so my g of h is going to be equals to 2h. And my g of 0, so either definition, when x equals to 0, is going to be taken 0 over here. So that what we get is going to be 0. All right, so then what we get is, again, a constant number 2. But on the other hand, if the limit is taken from the left-hand side, so then h is less than 0. And in this case, we know that g of h is going to be equals to 0. So again, we have got 0 minus 0 over h, and the answer will be 0. So now you can see that this left-hand limit does not equals to the right-hand limit. So then we see that g prime of 0, namely the two-sided limit of g of 0 plus h minus g of 0 divided by h, well, this guy does not exist. Okay, so in particular, this tells me that g is not differentiable at the 0. Okay, so this way we see the answer for part B is g is differentiable when x is non-zero, so we could also say that this g is differentiable on the interval minus infinity to 0, union with 0 to positive infinity. Okay, so for part C, well, we certainly have the formula g prime of x equals to 2 when x is strictly greater than 0, and g prime of x equals to 0 when x is strictly less than 0. Okay, I'll leave it to you to figure out why I can write g prime of x as 1 plus x divided by absolute value of x. Okay, so just try to track it using the same way as we did over here, and you will be able to see that this formula defines precisely the same thing as this piecewise function over here. Okay, so that concludes the problem 62. Now let's look at problem 71. So you were given a piecewise function with critical number 1. Well, to the left of 1, it will be defined as x squared plus 1, and to the right of 1, and including the point 1, f of x is defined to be x plus 1. And the question is f differentiable at 1? And also you need to sketch the graph of f and f prime. Okay, so there are two solutions for this one. The first solution will be very similar to what we have seen before. So we want to look at the differentiability of the function at the number 1. This means we need to look into the limit of f of 1 plus h minus f of 1 divided by h as h approaches 0. However, we notice that 1 is a critical number. So by our principles introduced before, so at the critical number, we need to look at the one-sided limits first. All right. So let's first study the case when h is approaching 0 from the right. So because h is approaching 0 from the right, so 1 plus h is approaching 1 from the right. So in particular, 1 plus h is strictly greater than 1. So this tells me that I'm supposed to use this formula for my f of x. All right, so that's going to be written as h approaches 0 from above of, okay, 1 plus h is simply going to be, okay, so f of 1 plus h is simply going to be 1 plus h plus 1. And f of 1 is simply going to be 1 plus 1. Okay, so you need to compute this limit, and you could see that this limit is precisely going to be h over h. Well, if you simplify the numerator, you will see that the only thing remains that's h. Well, and the limit of h over h is simply 1 in this case. All right, so this is the right-hand limit of the difference quotient. On the other hand, if we look at the left-hand limit of the difference quotient, so f of 1 will still be the same guy. So that will be 1 plus 1. But because now we are looking at the left-hand limit, so in this case, 1 plus h is less than 1. So that means we need to use this formula for the definition, or for the formula of f of 1 plus h. So f of 1 plus h in this case will be 1 plus h squared plus 1. And f of 1, that will still be 1 plus 1. So because for f of 1, we are supposed to use this formula over here. Okay. All right, so that's what we have. And I will skip the computation over here. So you do the computations by yourself. And what you will get in the numerator, this will be 2h plus h squared divided by h. And you compute this limit and you will get the number 2. All right, so you see that these two one-sided limits are not equals to each other. So this will tell me that f is not differentiable at the number 1. Okay, so this is the first part. And for the second part, we need to sketch the graph of f and f prime. Well, for the graph of f, we can start drawing it right away because the formulas are clear. But for f prime, aside from knowing that f prime of 1 does not exist, we do not know much at this moment. So that means we still need to compute a little bit. Okay, let's start with the discussion of the case when x is greater than 1. So in this case, well, when we try to compute f prime of x, so we will just use the same formula for both f of x and f of x plus h. And this is because my x currently is generic. Okay, so when x is greater than 1, my f of x is x plus 1, and my f of x plus h, well, we just use the same formula with the variable x plus h. What you get is x plus h plus 1. Okay, so then I will skip the computation. So at the end of the day, what you will get is precisely 1. So it's a constant. So this tells me that f prime of x is a constant function when x is strictly greater than 1. Okay, so if x is strictly less than 1, then, well, I will skip the definition part, but I will directly plug in f of x plus h and f of x in the first step. So, well, because when x is less than 1, my f of x is x squared plus 1. So because x less than 1 is a generic number, so I can simply use the same formula for f of x plus h. All right, so this is what I will be getting at. Okay, so I will skip the algebraic manipulation over here, and what you will get at the end of the day is going to be 2xh plus h squared over h. So this is what you will get after simplifying the numerator. And if you cancel out the h in the common factors, and then you let h approaches 0, what you will get is going to be equals to 2x. All right, so these is the derivative when x is strictly less than 1. So as a result, now we are getting a formula for f prime of x. So namely, f prime of x equals to 1 if x is strictly greater than 1, and f of x equals to 2x when x is strictly less than 1. Okay, so now we are ready to draw the graphs. Okay, so to make some space, let me move these solutions downstairs over here. Okay, so now let's actually start drawing the graph for f of x. So first, recall that x squared plus 1, so this is obtained from the parabola x squared. X squared is originally like this. So x squared plus 1 is simply shifting this guy upwards by 1 unit. So that's my x squared plus 1, but then we only need the part when x is strictly less than 1. So that's basically why we are only needing this part. So now let's draw it here. So it will be this parabola and together with this part, and it will stop at the number. So x equals to 1, and correspondingly, the limit is actually going to be 2 at this number over here. Okay, so that's the first part over here. Well, for x plus 1, so this is obtained by y equals to x, shifted upward by 1 unit. So, but because we only need the parts when x is greater than 1, so that's basically means, well, we need this part over here. So that means I actually have got a solid dot at this location, and then I will just draw a line with slope 1 to the right. All right, so this will be the graph of the function y equals f of x, well, answering the first part of the second part. All right, so this is what we have over here. Okay, so for the second part, let's just again draw the coordinate line. So the second part, the formula is easier. So when x is strictly greater than 1, the function is constantly 1. So that basically means my graph for f prime of x basically looks like this. So this is the number 1 over here. Okay, so on the other hand, when x is strictly less than 1, so my function looks like 2x, but because 2x is actually going to be a line of slope 2, but then passing through the point 1, 2, but then because we only need this part, and also we should have got a hollow dot over here. So that's how we get to this number here. So this is actually the line taking care of the other definition over here. All right, so this will be the graph for y equals f prime of x, and then so we notice that this graph will have got a hollow dot at the vertical line x equals to 1, and at the number 1, well, the derivative is undefined. Okay, so this concludes the first solution of problem 71, and you see that in this solution, we are basically following this definition of the derivatives very carefully. So we just investigate if the left-hand limit of the difference quotient and the right-hand limit of the difference quotient when x equals to 1, we just investigate if this limit exists. And we found that this limit does not exist. So f is not differentiable at number 1. Okay, so now let me introduce another solution. So the second solution is going to be way easier compared to the first one. The reason is the following important fact that can be proved after you see the mean value theorem. Okay, let's state this important and useful fact. So if first f of x is continuous, at x equals to a, and moreover, f prime of x exists everywhere except at x equals to a. So to decide if f prime of a exists, you could look at the left-hand limit of the derivative and the right-hand limit of the derivative. Okay, so if these two limits are the same, then you can conclude that f prime of a exists. Moreover, it is equal to the limit. All right, so this is the first situation. For another situation, if the left-hand limit and the right-hand limit, so both these guys exist, but they are not equal. So in this case, you can conclude that f prime of a does not exist. Okay, so this fact can be proved using mean value theorem, and I definitely will go over the proof in one of the supplementary videos. Let's now use this fact to the problem 71. So let's first start by looking at x prime of x for geometric numbers. If x is greater than 1, then we could get that f prime of x equals to 1. And on the other hand, if x is strictly less than 1, so then we can see that f prime of x, so this is going to be equals to 2x. And now, moreover, if you look at the limit of the f of x as x approaches 1 from the left, and then you see that this is going to be equals to the limit of x squared plus 1, and this is going to give us 2. So yeah, this is the left-hand limit of the function. And on the other hand, the right-hand limit of the function, this is going to be close to the limit of x plus 1. And you could see that the limit is also going to be 2. And moreover, this is precisely the same as the function value at the number 1. So then these three guys are the same, namely the left-hand limit and the right-hand limit at the function value at the number 1. These three guys are the same. Well, this basically tells me that f is continuous at 1. And because f is continuous at 1, and moreover, we have checked that f prime of x exists everywhere except at x equals to 1. Well, we see that f prime of x exists when x is greater than 1 and x is less than 1. Now, to determine if f prime of 1 exists, let's just look at the left-hand limit and the right-hand limit of these two guys. Yeah, you could directly see that the left-hand limit of f prime of x, so this is actually going to be the left-hand limit of 2x, and the function value will be 2, but then the right-hand limit of f prime of x, so this is going to be 1, and this is not equals to 2. So then from this fact over here, so we can conclude that f prime of 1 does not exist. Okay, so this is the second way of answering the problem whether or not f is differentiable at 1. And the conclusion is f is not differentiable at 1. Now let's work out number 72. So we will first use the definition of derivatives to solve the problem. So this is the solution 1. So first we look at the derivatives at the generic point. So if x is strictly less than 0, then we see that g prime of x is the limit of 2 times x plus h minus 2x divided by h. And if you compute the limit, and I will skip the computation over here, you will get a constant number 2. All right, so that's the derivative of g when x is strictly negative. Okay, so the next one, if x is between 0 and 2, so x is still a generic point. So when you compute the g prime of x, so you could just use the formula of g of x in between. So namely 2 times x plus h minus the square of x plus h minus 2x minus x squared. All right, I'll leave it to you to figure out the algebra. At the end of the day, what you will get is 2 minus 2x. Okay, so this is the expression of g prime of x when x is strictly between 0 and 2. Finally, if x is strictly greater than 2, so then g prime of x, so this will be the limit of, well, 2 minus x plus h minus 2 minus x, well, divided by h. So what you will get is going to be minus 1. Again, a constant number. All right, so these are the derivatives at the generic numbers. And now let's look at the critical numbers. If x equals to 0, then the limit of the difference quotient, so let me actually write it as g of 0 plus h minus g of 0. Okay, we need to compute this guy very carefully. First, look at the left-hand limit. So in this case, because h is less than 0 and g of 0 plus h is going to be used from this formula, so that will be 2h. So that will be 2h minus g of 0 follows from the same formula over here. So if you plug in x equals to 0, what you will get is going to be 0. All right, so it will be 2h minus 0 divided by h as h approaches 0 from the left. And what you will get is a constant number 2. Okay, so this is the left-hand limit for the derivative. For the right-hand limit, let's write the definition. So that's g of h minus g of 0 divided by h. Okay, so because h is now greater than 0, so we need to use this definition. So as a result, g of h is going to be 2h minus h squared. Okay, g of 0 is still going to be 0, and then the whole thing divided by h as h approaches 0 from below, and you will get the limit to be 2. Because these two limits are the same, so we can conclude that g prime of 0 exists, and moreover, g prime of 0 is precisely going to be 2. Okay, so this is the discussion at the number 0. At the number 2, so again, let's look at the difference quotient. So now x equals to 2, so it's going to be g of 2 plus h minus g of 2 divided by h as h approaches to 0. Well, okay, let's look at the left-hand limit first. So for the left-hand limit over here, because now 2 plus h is smaller than 2, so we need to use this formula for g of 2 plus h. And on the other hand, g of 2 invokes this formula over here. And if you plug in x equals to 2, so then you can see that g of 2 equals to 0. All right, so that's what we are going to get. So it will be the limit of 2 times 2 plus h minus the square of 2 plus h, and then minus g of 2. Well, g of 2 equals to 0. Okay, so this whole thing divided by h will have the limit. So again, I will let you to figure out the algebra. So the answer will be minus 2. All right, now let's look at the right-hand limit. So if 2 plus h is greater than 2, then we are supposed to use the third formula for my computation. So that means g of 2 plus h is now going to be equals to 2 minus 2 plus h. And g of 2 is still going to be 0. So that the whole thing divided by h, and the answer, I'll leave it to you to figure out, the answer will be minus 1. All right, so you see that these two guys are not the same. So as a result, you can conclude that g prime of 2 does not exist. Okay, so this is what we can obtain for g prime of x. And to make some space, I will just move every formula down here. And now we can write our conclusion over here. So g prime of x is going to be the following. So first, if x is less than 0, g prime of x equals to 2. So we can write a 2 over here with x is strictly less than 0. Okay, what happens when x equals to 0? Well, we also get the g prime of 0 equals to 2. So we could actually add an equality over here to say that this is precisely the g prime of x at the number 0. Okay, so between 0 and 2, so we have computed over here that if x is between 0 and 2, we have 2 minus 2x. All right, so that's what we have over here. And because the number at the number 2, g prime of 2 does not exist, so we don't need to worry about the number 2 over here. And finally, we just need to finish the problem by writing g prime of x equals to -1. So that way we write -1 if x is strictly greater than 2. Okay, so this will be the formula you are asked to get. And now let's actually draw the graph. Let me actually draw the graph down upstairs and also indicate that this is the final solution. Okay, so if we want to look at the graph of g, we first draw the coordinate, and let's actually see what we get. So well, y equals to 2x is going to be a slope looking like this, but we only need this part. So that's why we will only draw this number. So this will be a line of slope 2. Okay. When x equals to 2, when x is greater than 2, this is again a line. So this line will pass through the number 2, and it will have got a slope -1. Okay, so let's draw that down at this point with a line with the slope 2. Okay, finally, 2x times x squared. So this guy can be factorized as 2 times, so 2 minus x times x. So this is a quadratic polynomial. It's passing through 0 and 2 and on the x-axis. So roughly speaking, this looks like this. So we could actually draw it like this. But notice one thing, that at the point 0, the g prime of 0 exists. So that means, well, the parabola we are going to draw will have the tangent line coinciding with the y equals to 2x. On the other hand, at this point over here, we have to argue that the left-hand limit of the difference quotient is roughly -2. So then, yeah, the parabola will basically be tangent to this line with slope -2. So roughly speaking, the graph will look like this. Okay, so let's draw it like this. So you could see that over this number 0 over here, so everything is just smoothly connected, but over here there is a visible corner point if you want to draw the graph. Okay, now let's mark the annotations. So this is x and this is y. And then, well, what we have over here is 0 and 2, and the graph over here is y equals to g of x. All right, so that's the sketch for the graph of y equals to g of x. Okay, so the graph of g prime of x is easier. So because either it's horizontal lines or it's going to be strict lines. So let's see. So when x is less than 0, so g prime of x takes constantly 2. So that's how I have got this horizontal line over here. So this is the y coordinate 2. When x is greater than 2, so we have got a horizontal line, actually, which does not take the number -1 at this point. So then we have got a horizontal line, y equals to -1. So that's my graph over here. And finally, in between, so this is going to be 2 minus 2x. So it will pass through here, but then with the slope to be -2. So if you draw a line with slope -2 over here, so then this is actually where it will pass. So the limit to the left of 2, so this is going to be equals to -2 over here. So roughly speaking, that's what we have. So we need to draw over here. So this is actually -2, and now we connect it with a straight line. All right, so I think that will be the graph you are supposed to draw for this problem. Okay, so yeah, that will conclude the discussion for this problem using the first approach. Now let's give another solution using the important and useful fact we just covered in problem 71. We will still need to use the results we computed over here. So let me actually keep them here, but erase everything else, and including the graph over here. Okay, So then how should we proceed with that method? And this is my solution, not solution 1 anymore, solution 2. Okay, so remember the first thing to do is to check continuity at the critical number. So let's first check the continuity at the number 0. If x equals to 0, so then you could see that the left-hand limit of g of x, and you need to compute the left-hand limit of g of x, you need to compute the right-hand limit of g of x, and you need to compute also the function value at the number 0, and you want to check if these guys are the same. So this is how you check the continuity. Okay, so when x is less than 0, g of x is defined as 2x as x approaches 0 from the left. Okay, so then the limit is going to be equals to 0. And moreover, you see that this is precisely g of 0 because g of 0 is defined by the same formula over here. All right, so this is the left-hand limit and the function value. Now let's look at the right-hand limit. So x approaches 0 from above of g of x. So this means I need to use the second formula. So 2x minus x squared as x approaches 0 from above. And you can compute very easily that the limit of this guy is also 0. Okay, so this tells me that g is continuous at 0. Okay, here I should provide a side remark to here. So suppose you started out to check the continuity and you found that continuity does not hold. At the critical number c. So what happens if the continuity does not hold at the critical number c? Well, in this case, you don't even need to compare the left-hand limit and the right-hand limit of the derivatives. You could directly say, so in this case, f prime of c does not exist. Well, remember, if f is not continuous at the number c, then f is not differentiable at the number c. Okay, so this is something you need to keep in mind. So now we see that g of is continuous at 0, so potentially it might be differentiable. But then this can be checked by looking at the left-hand limit and the right-hand limit of g prime of x. So the left-hand limit of g prime of x, well, as we have computed over here, g prime of x equals to 2 when x is less than 0. So the left-hand limit of g prime of x is precisely the left-hand limit of 2, and the answer is 2. On the other hand, the right-hand limit of g prime of x, well, as we computed, when x is greater than 0, g prime of x equals to 2 minus 2x. And you see that the limit is 2. So from the equality of these two guys, we can directly conclude that g is differentiable at the number 0, and moreover, g prime of 0 equals to 2. All right, so this is the analysis at the number 0. How about at the number 2? So let's just repeat that. So if x equals to 2, let's first check the continuity. So as x approaches 2 from the left, limit of g of x is the limit of 2x minus x squared. Well, as x approaches 2 from the left, so this guy approaches 4 minus 4, and the answer will be 0. So on the other hand, when x approaches 2 from the right, so this is the limit of 2 minus x. Well, as x approaches 2, so this guy also approaches 0. And moreover, this is the same as the function value at the number 2. Okay, so this tells us that g is continuous at the number 2. Okay, so now let's look at the left-hand limit and the right-hand limit of the derivatives. So to the left of 2, so g prime of x, we have computed this guy to be 2 minus 2x. So then x approaches 2 from the left. What we get is 2 minus 4, and the answer is minus 2. On the other hand, to the right of 2, we saw that g prime of x is a constant function, namely minus 1. So the limit of a constant function is going to minus 1. And you see that these two limits do not coincide. So that way we can conclude that g prime of 2 does not exist. All right, so this is the application of the second method to draw the same conclusion. And as you can see, you do not need to worry about the difference quotient. All right, so this is what I want to say about number 72. Now let's look at number 74. So this is again an absolute value function, but the complicated issue is, well, here we have got two absolute values involved in the function expression. So this means, well, we need to be very careful about the choice of the positive and negative signs when we try to get rid of the absolute value. Okay, let's first notice the following. So first, if x is greater or equals to 1, then absolute value of x minus 1. So this is going to be non-negative number, and as a result, so we can get rid of the absolute value and directly write it to be equal x minus 1. But on the other hand, if x is strictly less than 1, so in this case, absolute value of x minus 1 is going to be equals to negative of x minus 1. All right, so this is what we should know regarding the first summand. And for the second summand, we know that if x is greater than minus 2, greater or equals to minus 2, then absolute value of x plus 2 is going to be equals to x plus 2 itself. And if x is strictly less than minus 2, then absolute value of x plus 2 is going to be equals to minus of x plus 2, and this will be minus x minus 2. Okay, so now we want to combine h of x together, so then we need to be worried about the intersections of each region. So then for h of x, if we want to write it as a piecewise function, so if we see that if both x greater than 1 and x greater or equals to minus 2, if you look at the intersection of these two regions, you will see that the intersection is precisely going to be x greater or equals to 1. So if x is greater or equals to 1, what we have is precisely x minus 1 plus x plus 2. Okay, so let's leave the simplification later, but let's just figure out what's going on for other choices of x. Okay, what's going on with x is less than 1? If x is strictly less than 1, then we know what's going on with the first guy. So if x is less than 1, so then the first guy with you have the negative sign over here. But regarding the second guy over here, there will still be two cases, and let's just look into the cases one by one. So if x is strictly less than 1, but x is also greater or equals to minus 2, so in this case, my h of x will be this guy plus this guy. And let me simplify the minus x minus 1 as minus x plus 1. So then if my x is strictly less than 1, but greater or equals to minus 2, then what I'm getting at is minus x plus 1 plus x plus 2. All right, so that's what my h of x is in the middle interval. Finally, if x is less than 1 and x is also less than minus 2, as you can easily track, the intersection of these two regions is precisely x is less than minus 2. So in this case, well, my function is going to be this guy plus this guy. So what we will get is minus x plus 1 minus x minus 2 if x is strictly less than minus 2. Okay. So now we could further simplify this guy as 2x plus 1 if x is greater or equals to 1. And in the middle guy over here, we get the number 3. So this is the function where x is between minus 2 and 1. And finally, when x is strictly less than minus 2, and then what we get is minus 2x minus 1. So that's my expression of h of x. Okay, so this is the formula for h. And now how do we find the formula for h prime? Well, the idea is basically the same as before. And let me just go over this problem using the second approach. And I will just skip the first approach. So if x is strictly greater than 1, so this means x is a generic number. And in this case, you can compute h prime of x using the same formula for h of x. So namely, h approaches 0. I'd better not use h over here. Let me just use another notation. Limit of s approaches 0. And then this will be h of x plus s minus h of x divided by s. Okay, h of x plus s and h of x, well, they both come from this formula. So what I will get is 2 times x plus s plus 1 minus 2x plus 1 divided by s. Well, I will leave the algebra to you, and then at the end of the day, what you will get is precisely 2. Okay, so this is what happens for the genetic number that's strictly greater than 1. Okay, so now let's look at another genetic number. So when x is between -2 and 1. So in this case, h point of x is going to be the limit of s approaches 0 of, again, so it will be h of x plus s minus h of x. But in this region, so the function is constant. So then this will give me 3 minus 3 divided by s, and the answer will be 0. Okay, so we know that h point of x equals to 0 when x is sitting between -2 and 2. Finally, if x is less than -2, so you just do the similar computation, but now just use the same formula for h of x plus s minus h of x divided by s. All right, so this is actually going to give me -2 times x plus s minus 1 and minus -2x minus 1 divided by s, and the answer, I'll leave it to you to figure out, the answer will be -2. Okay, so this is basically what we can see from the genetic points. Okay, now let's look at the critical number. Let's start with x equals to 1. So then in this case, let's first check the continuity. So then we can see that the limit of x approaches 1 of h of x, if we take the left-hand limit, so that means I need to use the first formula. And in this case, what I have is the limit of 2x plus 1 as x approaches 1. So then the answer is 3. And on the other hand, if x is approaching 1 from the left, then we are supposed to use the second formula, but then this is actually a constant function, so we can directly say that the limit is going to be 3. All right, so, and moreover, we know that the first expression also gives us the function value. So this is also h of 1 as well. All right, I need a plus over here. Okay, so then this tells me that h is continuous at the number 1. And now, so in order to figure out whether or not my function is differentiable, so all I need to check is if my left-hand limit of h point of x equals to my right-hand limit of h point of x as x approaches 1. So for the left-hand limit, so we see that we are supposed to use this formula, and we see the left-hand limit equals to 0, but the right-hand limit is different. So x approaches 1 from the right, so we are supposed to use this formula we'll take over here and see that the limit is precisely 2, and they are not equal. So as a result, h prime of 1 does not exist. Okay, a similar procedure happens for the other critical number, namely x equals to -2. Let's just do it very quickly. So the limit of the function to the left of -2, and then this is going to be the limit of -2x minus 1 as x approaches -2 from the left. And the answer for this is going to be 3 again. On the other hand, the limit of x approaches -2 from the right of h of x, because in this case, we see that h of x is constantly 3. So this is going to be equals to 3, and moreover, it's going to be equals to the function value at the number 2. So this way we check that h is continuous at -2. All right, so now we just need to figure out if the left-hand limit of h prime of x and the right-hand limit of h prime of x is the same. So as x approaches -2 from the left, so you see that the function is, well, h prime of x is constantly -2, so then the limit will be -2. And for the right-hand limit at number 2, so h prime of x will have the limit 0, because again, it's a constant function, and these two guys are not equal. So as a result, h prime of -2, so this also does not exist. Okay, summarizing what we have obtained above, we get h prime of x. So this is going to be equals to 2 if x is strictly greater than 1, and then 0 if x is between 1 and -2. And finally, it's going to be equals to -2 if x is going to be further less than -2. All right, so that's my h prime of x. And notice that h prime of x is not defined at those critical numbers. And now let's actually draw the graph. So the graph for this function is pretty easy to draw. Let's actually start with the h of x. So because this is basically 3 lines. So first, when x is greater than 1, so the function looks like 2x plus 1. 2x plus 1 will pass through the number 3 at the number 1. So moreover, it's going to be a line of slope 2. So this hints me that I should probably move my x-axis a little bit downward so that I can draw more to scale. So this is going to be at 1, and this is going to be my 3. And then my function is passing through this point, and moreover, the line is actually like a line. Well, the line is going to be of slope 2. All right, so this is the function when x is greater or equals to 1. Okay, so between -2 and 1, we see the function is constantly 3. So let's just get rid of this dash and then draw a horizontal line, namely y equals to 3, passing through, not this way, passing through these 2 points, namely 1, 3 and -2, 3. So these are the 2 points they pass it through. And finally, when x is strictly less than -2, so then we see that the function is actually -2x minus 1. So this will be a line passing through -2, 3, and moreover, it will have got the slope to be -2. All right, so roughly speaking, the graph looks like this. All right, so then all we need to do is to finish the annotation and declare that this is my graph for y equals to h of x. All right, so that's going to be the graph for h of x. And now for the function h prime of x, let me draw the x, y coordinates. So, well, this is just going to be 3 lines. So if x is greater than 1, then the function is constantly q. So this is my 1 and this is my 2. So then the function will basically look like this. And let's draw that. So this is 1 and this is 2. And h prime of x avoids this point, but then after this point, it will be horizontal line y equals to 2. So okay, between 2 and -2 and 1. So this, let's say this is -2 over here. So then what we have is going to be another horizontal line like this, but moreover, it will be avoiding this point, the endpoints over here. And finally, when x is further less than -2, so then we will have got the graph basically look like this. So this is going to be the y coordinate -2. And then, well, the graph of h prime of x over this interval will simply be the horizontal line stretching to the left. All right, so that this will be my graph for y equals to h prime of x. And so we will just finish this problem by the annotation. Okay, so this is all I want to say about problem 74, and probably you should try to use the first method to go over these steps over here. So that might be helpful for you to understand these techniques, and you can make a choice which one do you prefer. All right, I will conclude this supplementary video by discussing the last problem, number 81. So for this problem, f of x is given in this form. So when x is less or equals to 2, so f of x takes x squared. When x is strictly greater than 2, we have got a function with 2 parameters, m and b. So f of x equals mx plus b. And we need to find the values of m and b that makes f differentiable everywhere. Okay, so just like what you have seen in test 1, it's very important for you to check the differentiability everywhere else first. So let me actually start by looking at the generic points. So if x is strictly greater than 2, then we see that f prime of x equals to the limit of f of x plus h minus f of x. And because my x over here is a generic number, so then I can use the same formula, namely x squared, for both f of x plus h and f of x. So f of x plus h, that will be x plus h squared. And f of x will be x squared. So I will leave it to you to compute this limit, and the answer you will get is going to be 2x. All right. So on the other hand, if x is strictly less than 2, so then f prime of x is going to be the limit of f of x plus h minus f of x divided by h. But because now h is again a generic number, so I will just use the formula mx plus b for f in both expressions. So f of x plus h will then be m times x plus h plus b, and f of x will be mx plus b. And again, I will leave it to you to figure out the algebra, and at the end of the day, what you will get is going to be the number m. All right, so these are the formula for the derivatives at the generic numbers. And now let's look at the critical number. Okay, so let me use two methods as we introduced before to analyze the derivative at the number 2. So for the first method, if x equals to 2, so let's look at the left-hand limit of f of 2 plus h minus f of 2 divided by h. Okay, so as h approaches 0 from above, 2 plus h is going to be larger than 2, so that means I need to use mx plus b for this formula over here. But on the other hand, if x equals to 2, then I'm supposed to put f of 2 to be 2 squared, namely 4. All right, so that's what we should do. So f of 2 plus h, that will be m times 2 plus h plus b minus 4 divided by h. Okay. So this one needs to be simplified, and yeah, you could simplify this fraction as follows. So the numerator is going to be 2m plus mh plus b minus 4. And if the whole thing divided by h, you can actually separate it into two parts. One part is going to be this fraction, and the other part will be the rest. So what we will get is going to be mh divided by h, that will be m. But the other part is going to be 2m plus b minus 4 divided by h. Okay, now let's look at what happens if h approaches 0. So if h approaches 0 from above, so then the first guy over here approaches m, so there's no trouble for this. But if h approaches 0 from above over here, so then this is going to be 0 in the denominator. So on top over here, if this guy turns out to be a positive or negative number, what we have is positive infinity or minus infinity. Okay, so therefore, what we can say is the following: to make sure the limit exists, it is necessary that the numerator for the second fraction to be 0. So 2m plus b minus 4, this has to be 0. All right, so this is actually what we can say about this. And in this case, the right-hand limit. So the right-hand limit of f of 2 plus h minus f of 2. So this is actually going to be equals to m in this case. Yeah, provided that the numerator for the second fraction equals to 0. On the other hand, if you look at the left-hand limit, then 2 plus h in this case is going to be strictly less than 2. So that means we need to use the x squared formula. So f of plus h, that will be 2 plus h squared. And then f of 2 is going to be 4. So I will leave it to you, figure out the limit. And the answer at the end of the day, you will get number 4. All right. So because f prime of 2 exists, so this means, so first these two limits has to exist, and then we see that, well, this limit exists if the numerator equals to 0. That's how we get the first equation. Moreover, these two limits have to be the same, so this basically tells me that m equals to 4. So that way we get the equations, well, 2m plus b minus 4 equals to 0, and meanwhile m equals to 4. So that way we will be able to solve b. So b is going to be equals to minus 4, and m is going to be 4. So how do we see b equals to minus 4? So because this one becomes 8, and 8 minus 4, this becomes 4. So b plus 4 equals to 0. So that way you will get b equals to minus 4. Okay, now let's use the second method to study this problem. So remember, for the second method, we need to start by checking if the function is continuous. So if x equals to 4, let's look at the left-hand limit and the right-hand limit of the function. So for the left-hand limit, so this is going to be the limit of x squared. And the limit is going to be equals to 4. And we know that this is also the same as the function value at the number 2. All right, on the other hand, the right-hand limit at the number 2. So this is going to be the limit of mx plus b as x approaches 2 from the right. And then what you will get is 2m plus b. Okay, since f is differentiable at 2, so in particular, so this tells me that f is continuous at the number 2. So this will tell me that 4 is going to be equals to 2m plus b. So that way we get our first equation. Okay, now let's look at the limit of the derivative. So let's start by the right-hand limit. So that if x is greater than 2, then f prime of x equals 2x. So the right-hand limit of f prime of x is the right-hand limit of 2x as x approaches 2 from the right. And the answer will be 4. On the other hand, the left-hand limit of f prime of x as x approaches 2 over here. So this is simply going to be the left-hand limit of the constant function m. Well, that way we see that the left-hand limit is precisely going to be m. Okay, so f prime of 2 exists implies that these two guys are the same, so that what we get is going to be m equals to 4. Okay, so together with this guy over here, what we get is 4 equals to a plus b, and then as a result, b equals to minus 4. Okay, so this finishes the discussion of number 81, and that concludes the supplementary video for lecture 8.